I would like to thank you for joining me today and to give me the opportunity to present you this. So it's not it's going to be a single work, but it's going to be a kind of a journey on the updated journey on the open cluster field and the impact of machine learning in this particular field. So we start, of course, from scratch. So we live in a spiral galaxy. We know for quite a long time. Not that much, actually. And we know it. We observe many other spiral galaxies, but our galaxy is quite different because we have a different point of view on it. So we are looking at a spiral galaxy inside a spiral galaxy, of course. And so we can study in details more details about the structures of our galaxy. And there are a lot of open questions that we need to answer. And of course, grows up also with the recent discoveries. And we have extraordinary laboratories to do that are called open clusters, that are very beautiful astronomical objects, as you can clearly see from this picture. But let's start from the definition of what is an open cluster. An open cluster is simply a group of stars that has been born together, so they share the same age and chemical composition, and they should also be bounded by gravity. So this is a clear, let's say, definition that we need to remember well when doing this presentation. And why they are important? Why are open? What? Why are they called open? Yeah, because historical point of view. It's like globular and open, because open clusters seems like less bounded than globular ones. So globular seems to be bubbles of stars, and they are like in an insulated environment. Open cluster seems like more, you see from there, like inside the field of stars, but they are actually clustered. Why they are so important? Because for many reasons, but one of the historical things is that it's possible with them, with their photometry, to infer age, metallicity, and distance of their stars in a precise way, at least more than in single star case. So as I say to you, there are multiple fields that are interested in open clusters. Open clusters can trace spiral arms. Here you see the maps from André and the one from Eloisa Poggio. They can trace the metallicity gradient, so the fact that the metallicity goes down, so you have less metals in the outskirts of the galaxy. And you can also ask to yourself something about the star formation of the galaxy, because here you have a very beautiful plot where all the dots are open clusters, and you have the galactocentric distance, and here you have the height on the plane. So here you have the sun, and if you can see here from the purple dots that are only the youngest clusters, you kind of see a stop around 11 kiloparsec from the center. So you may think, okay, probably the star formation in that region is lower than in our region or in the inner part. Then, of course, the most famous things that you can do with open cluster is to test stellar evolution theories, but you can do also the reverse of this. So you can use evolutionary theories and particularly isochrones to infer the parameters of open clusters. You have also to study the dissolution process of these bounded structures. Like you can see in this plot, it's the same as before, just colored the old clusters. And as you can see, they distributed above and below the disk. And so seems to be the dissolution process seems to be correlated to the density of the environment. And of course, you can also study the internal dynamics of these clusters from their tidal tails. And as recent works suggested, they may also indicate something with gravitational theories. So in particular, as you can clearly see here, they say that Newtonian dynamics predict different populations with respect to micromian dynamics of the tails of the clusters. So multiple different fields, you can see that ranges from a bigger scale to a smaller scale. But all they have something that is very important and in common. That is, you need to create catalogs of these open clusters with a high purity, and if you can also high completeness, or at least know the selection function. You need for sure to have accurate membership, so you do not want to have into your cluster stars that do not belong to them, or fewer stars than the ones that should belong to the cluster. If you think, for example, at the tidal tails studies. And of course,
sorry, what's the difference with that and purity?
What?
What's the difference between membership and purity?
Yeah, this one is the high purity of the clusters catalog. So you do not want to have false clusters inside. So something that is clustered just for chance. You want something that is a real cluster, that is bound by gravity, not something that is like clustered in the parameter space, but not a real cluster. We will see it in a while. Why is it so important? And for that cluster that you find, you want also something that is like accurate, the membership, so it will not contain contaminants for that. So we will see that with automated tools, these two are very tricky to reach, and we are not at the optimal point right now. And the last thing that is also important is you need to derive precise parameters for these clusters to make all the studies that we saw before. So, of course, a big impact on this field has been given by the mission Gaia that tries to actually makes a beautiful 3D map of the star of our galaxy, and for which we have like the motions, luminosity, temperatures, composition, and maybe other physical parameters. And the point is that now we are dealing with a lot of data, because we are dealing with 1.5 billion sources in the last data release, and that probably will increase a lot in the data release, the next data release. So we are having a problem with the big data problem, as all the world is encountering right now. So what we will ask to ourselves is that how we can find clusters in this ocean of data. And because hidden here, there is a cluster that, of course, you cannot see in the first picture. Because to look at clusters, we need to look at a different space. That is the so-called 5D space. That is simply a 5D space. So you may think that if the stars are bounded by gravity and they've been born together, they should be close by to each other. So you are looking in the physical space, and so you see the position in the sky. They should be nearby, and the parallax, so the third dimensional space. But by the fact that they are bounded, they should move together with respect to all the other stars that are unbounded. And so if you sum the spatially constant and the coherent motion of stars, you probably find something that is likely to bound. It is likely to be bound, so probably an open cluster. And of course, if we look again at this picture, it's just a zoom in of what you saw before. In this beautiful cluster is NGC 3293. You can see, okay, maybe it's clustered in this space of the sky position. But what really emerges is the fact that when you look at the proper motion, so how these stars are moving, you can clearly see that this group of stars is moving together with respect to the field. So these ones are probably bounded, and so that's open clusters. So you say, okay, fantastic. So we have a method to extract open clusters. Yes, but with 1.5 billion of sources, you need something that is automatic, that do the things for you. One thing that is fairly famous and commonly used is a machine learning algorithm that is called HDScan. You can read by yourself the extend name of this algorithm. That is an argument that is not that complex to understand, but is too long to explain here. So long story short, it's just searching over density in the data with some flexibility on their density. So you can both find something that is like more sparse, but is still an overdensity in the data, and something that is very, very clusterized. Sorry. And as all the algorithms of the world depends on some parameters that you need to impose to make it work better or in a more efficient way. And this one of the famous parameters that really lead its efficiency is the called minimum cluster size. So you may think, okay, you just infer from theoretical point of view, observational point of view, the minimum cluster size, you obtain the best parameter. That's a tricky thing, because this thing cannot be inferred directly, because it's something on the algorithm and is not something from physical or observational things. So we can discuss like all the day on this algorithm, but it's simpler to look at it at work. So here I just generate a field of stars that are not clustered and some clusters, 4 clusters. Here you have the fact that here, this one is more sparse than this one, and HBScan can realize when well with this type of clusters.
You give it the 5.
No, these are just a 2D example. Otherwise, it's very complex to visualize it. So this is thanks for the question. Yeah, this is only a 2D example. You can easily extend this to 5D, 6D, whatever you want. HBScan is very powerful for this reason. So then you remove, of course, the labels and let HBScan searching for clusterization of data using like a thing that you suggest, like minimum cluster size of 2. You see that it's dimensionless because it's a parameter of an algorithm. And this is what HBScan looks like with this run. So each colored dot belongs to a cluster. So for example, this one is all labeled as a cluster. This one is all labeled as a cluster, and so on. And here you have the crosses where the stars do not belong, or these points actually do not belong to any cluster. So what you can clearly see from that is that HBScan is finding too many clusters, simply. So you need to adjust the parameters. So it's just like, I think that's trial and error. At a certain point, you find the best compromise. And this is a compromise because you find the 4 clusters of the beginning that you inject in the data. But the problem is that, as you can clearly notice, is the fact that you have multiple problems here. You have false positives that are the things that I tell you in the beginning. So what they are, the contaminants of the both samples are the false positive of clusters. So that's why you're asking for high purity. And you also have false members. These stars, points again, sorry, do not belong to cluster 3 in the beginning, but they were associated to that from the algorithm. So you can clearly see that, yes, HBScan is very powerful, but you need to tune the parameters of this model. And usually what you do is to have like a well-known clusters that we discovered like 20 years ago and even more. And we just search for them in Gaia, and we select these parameters that are the best ones to efficiently retrieve this one, reducing the false positives, but reducing, not canceling, because you still have it. Because one of the features that is not good of HBScan is to generate false positives. So here you have also you need a validation of the candidates that are exit from that are outside. Yeah, sorry, the output, sorry, of the algorithm. So you need it's crucial to have a validation. And another thing that is very important that is connected to how we define an open cluster is the fact that this algorithm deals with distances. And so you need to search in a 5D space that is standardized. So in this way, you are losing physical information. So what you are finding actually are clustering of data, but not real clusters. They are candidates because they are overdensities in the data. As you saw before, you have false positives, but also things that are well clustered could not belong to something that is a real open cluster. So you need the validation is critical. The problem is that now you will assume that I switch the slide and give you the answer to this. The problem is that the answer is not here yet. I'm currently working, as many other persons in the world, many other researchers that are more advanced than me, but we do not have a clear criteria to determine these false positives of open clusters. So this leads us to think that inside our catalogs that are present what I personally call HBScan monsters, that are these objects here. You see, this is style 6046 is in a lot of papers. It has been discussed a lot. Is inside a lot of catalogs of open clusters, but is clearly not an open clusters. Here you see the spatial distribution of the members that you are extracting squares from the sky. something that is very unlikely to be a cluster. And also, if you look at the parallax, you have a wide range of parallaxes. And if you translate it into the physical dimension of these things will be like big, like 10 kiloparsec, something that is the galactic disk. So what is finding HD scan is actually something that is co-moving, but this is the co-moving of the disk. So it's finding field stars that move together because they are field stars that belongs to the field. And you could, but the problem is that the number of these objects is.
No, but how do you know they're false?
These ones are biological things. This one is false biological because you have like this thing is not a cluster for sure, because if you translate the parallax into the physical dimensions, this thing is big as the disk of the galaxy. So probably is not. It's finding something that is an overdensity in the data, because of course also the disk that is co-rotating has a peak in the data. So HDScan is finding that peak that by chance, by multiple factors, that could be also the fact that you are losing the physical information. So it's just searching for a point, a clusterization of points. If you are far away, as in this case, you have like less stars, and so these things should appear like are just overdensity in the data. The problem is that is this one. These monsters pass all the metrics that we have right now to distinguish between these clusters. Of course, you can say, okay, I can like study their physical dimension, but it's not that easy because you have like true clusters that are far away, and so by the errors of the parallax, they should be like very big, but you know that for the errors are not that big, that are actually clusters. The problem is that if you look at all sky search around the galaxy, you are dealing with different environments with a lot of different characteristics. So sometimes you ending up with this without knowing how to remove them.
There's something that's not. What's
yeah.
The input of the code and the output? The input are images?
No, the input are points in a 5D space. Each star of Gaia is in a 5D space, like these ones. You see that are sky position, proper motions, and parallax. And so you imagine the 5D space is finding clusterization, like in the 2D space, but it's just that.
So somewhat like coordinates of 5D space.
Yes, but you need to standardize them. So you need to remove the physical position because the thing is like a difference in 0, 1 in radial ascent would not correspond directly to 0, 1 in parallax. So you need to rebalance the things because it's dealing with distances. So you need to like standardize the distances. Otherwise, it's finding overdensity only because the parallax ranges from 0.1, 0.2.
And what's the output?
The output is like a series of members of stars that belongs to some clusters. As you saw before, this one, this is the output. The output is like an array with the coordinates of the objects and a label that says to you, this is a cluster. That's the output of the HD scan.
Can you show the next slide?
Yeah, sorry. No, this one or the other one?
Yes,
This one.
So, Gaia is the cluster.
No, this one is not. It's labeled as
No, it's labeled as a cluster,
yes.
right?
Yes.
But it's a huge range of parallax.
Yes, exactly.
Why the range in parallax is not limited when you want to find a cluster? Why did it pass the selection criteria?
Because the selection criteria is up to now. The problem is that you're just seeing one of the monsters. This one has some features, some characteristics. Sometimes you have monsters like that that have completely different behavior.
I understand, but particularly this one, the people
Yeah.
don't let you get. I do not understand
Yeah.
why this huge range of parallax was not enough to remove some of the stars that are.
Yeah, because the matrix that is being used for like you have like a metric that is very famous that is based on the dispersion of proper motion velocities. You are saying that if a cluster is a real cluster, the dispersion in proper motion should not be bigger than some value. The fact that this thing, from this point of view, you can barely see it, but I know the relation at this parallaxes. This pass well the cut. So you need a cut in the physical dimensions. But if you make a cut in the physical dimension, you end up excluding a lot of clusters that are actually clusters, but are detected at small parallaxes, so the errors are big. So every time that you try to have a clear cut, you end up excluding true clusters and including false ones. So it's very tricky because the problem is that this is my belief, so I do not have a clear idea on that, but my belief is that it's not enough one cut, two cut, three cuts. You need to extend the dimensions of this, and maybe you will find somewhere where these points are all on the edge of something. But right now, it's kind of impossible. It's not impossible. You can look at one by one. Yep.
For instance, if by eye, you take this cluster, you will be immediately know that there are stars that are outliers.
No, I will say that this thing is not a cluster at all, because the physical dimension of these parallaxes are realistic.
Well, we can discuss.
Okay, yes, yeah, for sure. So yes, but by eye I will discard it.
Some of the stars there.
No.
2000.
Yeah, but you need to remove all of them probably. Another problem that is like very common is this one. Is that you tune the parameter, the algorithm to reproduce well-known clusters. The problem is that you're using the same parameters in all the galaxy. So the problem is that you are ending up with zones where you are close by and not well populated. And you use the same parameter as in very distant part of the galaxy, very highly distinctive. That's for me the biggest problem. So probably using HDScan, you cannot use the same parameter for all the galaxy, but you need to distinguish between different zones in the 5D space, of course, and tune the parameters zone by zone. That's my guess. Doing that is fairly complex, but yeah, I'm aiming also to do that in the future, of course. So okay.
Yeah, if you do it by dividing a bit your space, also in parallax, then you won't get this kind of problem, right? Because this is if you're getting the full galaxy into your HD scan.
Yeah, is you having a full probably a full spiral in. Yeah, but it's very complex the problem because you are dealing at 5D space. And the real problem that I'm seeing is the removing of physical things. Because if you remove it, the tool is not sensible anymore to something that is like makes sense or not. And this is completely driven by the parameter that we saw before, so the cluster size. This thing is just an asterisk in the data, only because probably these things I saw also where it is, this thing. It's like in a zone that is highly distincted. So the errors are higher. And so HDScan deals with errors also. And so HDScan just say, okay, these are big errors, but it's fine. It's a cluster. Only because it's not as the others, only because the errors. So it's fairly complex. So the bottom line of all these things is that machine learning things are very powerful, but sometimes they have enormous pitfalls, especially dealing with a lot of things. Now we will see in a moment. Another problem that you want to deal with when you are studying open clusters is the parameter estimation of these things. And so we know for sure that color-minded diagram contains all the information on age, metallicity, extinction, and distance of the clusters, and so the stars of the clusters. And what is a common technique to fit theoretical isochrons to observe the data, as you can see here, done by Leila Casanitera in 2023. The problem is that he's usually performed by hand and case by case. And again, the problem is that now with Gaia, we are having a lot of problems of the number of things that we are detecting. So here you have a beautiful plot by Parent and collaborators 2023 that shows you the number of catalog open clusters that are not real catalog open clusters, reported as open clusters, as a function of the year. And you see here the line that shows you Gaia. So the number of clusters rise up to like 10,000. We know, as we already know so before, that part of them are false. There are some estimates on that. Somebody says that are the 20%. Somebody more pessimistic says that they are probably the 40% of them. The problem is this one. You cannot look at each cluster. And the problem will escalate a lot when moving to Gaia DR3, because you will have a lot of more data, so the cluster will be more and more. So it's a huge to find a clear cut to distinguish these clusters. So regarding the parameter estimation, again, you have another problem. You need, again, an automatic tool to do this analysis. And this tool should be fast, of course, and reliable, because you are dealing with a lot of clusters, but you do not want to lose precision for sure. And of course, should be prepared to new missions and use all the available data in the best way possible. So, possible solutions. This one has been proposed by Diaz and collaborators in 2021. And this like what you call classical method is like to minimize a likelihood function. So you are fitting an isochron, finding the best fit parameters, and you say that these ones are your estimates. The problem that in these problems, the parameter space is too big, and the computational cost is too high. And the fact that you are handling with a lot of new clusters, the problem just increases. So to avoid this problem, they try to reduce the parameter space by assuming priors, like the metallistic gradient that we saw in the beginning, and also the extinction map. That is just a map that tells to you that at some distance in that direction of the galaxy, you find some extinction. The problem is that the estimate that comes out from this analysis, you cannot use for sure metallicity and extinction because you assume them. And so it's not perfect, but still we have a lot of problems with the computational cost of this for 10,000 clusters. So, of course, I'm here to talk with you with machine learning things. So, of course, now we will be an algorithm of machine learning that is fairly famous, that is an artificial neural network. That has been the proposed solution. So what if we do not fit an isochron, but we teach to a neural network how to recognize the patterns in the color magnitude diagram that scales with the different parameters that we know from stellar evolution theories? An artificial neural network, basically simple assumption looks like that. So it's a series of layers that are composed by neurons that are connected with the others. Usually you have an input layer and then a series of hidden layers and then an output. So the input is what you want to inject into the neural network. Then you have a series of hidden layers and neurons that has some weights. And then you have the output. The output is simply a linear combination of the inputs and all the weights on the path. So when you are designing an artificial neural network, you are asking to yourself what you want to do. In this case, we want to detect the breed and color of a cat. And then you ask to yourself, what is your training set? So you want to use real pictures, or you want to use simplified pictures of cats? You want, I don't know, paints of cats, whatever you want. And then you have this critical procedure that is called feature extraction, that in which you need to ask to yourself, what is something that defines a cat as a cat? Because, as you can clearly see, the input layer of a neural network is a 1D array. So you need to translate something that is inside your training sample into 1D array. That can be composed whatever. If you are analyzing images, you will translate the matrix of an image into 1D array with some algorithm. That's a crucial point, because in this procedure, you can lose something that is really important, or you just lose some information that, and you do not recognize it. So recently has been proposed again other two solutions for this. These are the only, there are three actually, the models with artificial neural networks, because there are also mine, of course, but I'm here to present you this. But these are being proposed in literature. And again, you see that they made like slightly different choices into the training set. So Tristan in 2020 was the first one that tried this. Trained the neural network with well-studied clusters, real clusters. And on the other side, Emily last year used simulated synthetic clusters. I prefer the path of Emily because injecting well-known clusters into an artificial neural network, you are teaching to the neural network that the only things that exist in the universe are the one that we already discovered. That is something that I do not like a lot. I would like to teach to the neural network something that we common belief on clusters, so theories, and then finally this part. And then you have the critical part of feature extraction. How they transform a color magnitude diagram into 1D array. They compute a 2D histogram of the color magnitude diagram, and they feed it, so they compute an image of the color magnitude diagram, and they feed it at a convolutional neural network that he used, for example, to image recognize things like that, and translate it into a flat array. We do not go into the details.
Why not stick to a CNN until the end?
This one, because the CNN just produce you this path of features in injection in this way, because they try to, I know for sure that they try to do that, but they do not accomplish the mission. So they just use this thing to think, okay, we can use something that pre-proceed the data as a convolutional neural network that convolves all the information in 2D in 1D, and then feed to an artificial neural network. It's just a coupling of things. And this gives you an idea that the feature extraction is like a separate procedure that you need to think of. Of course, I'm here to take this seminar, so I will present also my solution to this that has been published like in January this year. And so our solution is like to use the training set of synthetic clusters. As I told you, I like to teach to the neural network something that is my theoretical beliefs on clusters. The feature extraction has been made with a new thing that is called code tree. That is an algorithm that I will show you in a while. And the output that we want to obtain is the age, metallicity, extinction, and distance of the cluster. What is new is the fact that we ask to a neural network also to estimate the metallicity of the clusters. That is sometimes really tricky with photometry.
When you do the synthetic cluster, do you like model noise and stuff as well?
Yeah, exactly. You we can like discuss a bit more afterwards to how we build the synthetic, because there are like multiple things to discuss. If you want like the synthetic to be more realistic, or you want like to be like isochrones. I would like to have like this like something that is theoretical, but with some errors from the photometry, and that's it. Because I want an isochrone. Because at the end, I want the neural network to recognize an isochrone that is like a bit noisier, but is an isochrone. But does not make a lot of differences because of the feature extractor. Because the neural network is not seeing this thing, cannot see this thing. So we use a quad tree to extract the information from the color magnitude diagram. So the quad tree is like it's basically a tree data structure that is used to represent things that are in 2D in 1D. But basically, things that are in 2D. So it's a tree data structure. So you start from, it's a series of levels. So you have the first level, you just divide the space in 4 different quadrants. And in each quadrant, you want to have the same number of points in that. Then you go to the second level. So you go deeper, and you divide each quadrant in other 4 quadrants. And you repeat this thing with the same rules. At the end, you're dividing again the quadrants that you find in the second level in other quadrants. And at the end of the procedure, you ending up with this structure. if you see the boxes here that are generated by the code tree, you can clearly see that code tree is tracing the sequence. So what we do, we extract the coordinates of these boxes. And so now we will fit to the neural network the position of the sequence in the color magnitude diagram. Then I will show you why it's better than in the other case. So the whole pipeline is like that, looks like that. So you have your color magnitude diagrams. In this case, we also use other photometry, not only the one of Gaia, we use also the infrared photometry from GMAS here to have disentangle between the degeneracies of the 4 parameters. Then you compute the code tree, and then from the coordinates you have the input layer. Here you also have the mean parallax of the cluster because it's a strong tracer of distance for nearby clusters, and you feed it to a neural network, obtaining what you want. But of course, you need to use some data to analyze. We use a sample of clusters that has been presented by Hunt in 2023 that performed like a blind search in Gaia DR3 is the biggest homogeneous catalog, biggest homogeneous search, and used HB scan, the one that we just saw, and they recover like 7,000 candidates of cluster, because as we saw, also in this thing, you have the monsters that we saw before. So we further select is with only stellar association that has more than 10 stars. It does make more sense to me and also helps the neural network to work better. But before that, as we know, machine learning algorithms are powerful, but with some pitfalls. You need to perform sanity checks that are not commonly performed. You find like articles on machine learning techniques. Sometimes the lack of this part that is very important. You need to perform a sanity check. You need to start from an assumption or like a statement that is like artificial neural networks are good interpolators, but bad extrapolators. So what you want is the fact that your data is fully contained into your training set and not this situation here. Because in these points, the neural network will tend to or recover to the borders of the training set, so delivers you something that is completely out, or worst, extrapolate. That is something that you do not want to do to a neural network. One thing that is really important is that these spaces are not the parameter spaces, are just the input. So you compute the input layers that you want to feed to the neural network, and you perform this analysis. So is before trying to do anything with the neural network. So here you have, I know that it's a bit complex, but it's very important. So the input layer is composed by create a space of 190 dimensions, because you have 190 entrance of this. So each input layer will be a point in this gigantic space. You would like to see the plot before. So you want an area and see where are the data and where are your synthetic clusters. So to do that, you need to reduce the dimension of the space. And to do that, we use a t-SNE map. That is another algorithm again. That simply what is doing is just iterating. So he removes a dimension and remap the distances in that dimension in the other remaining dimensions. And you continue like that. In the end, up 2 points that are close by in the 2D plot, where the closest one in the higher dimensional space. So here you see the color-coded plots, so points, sorry, are the synthetic, so our training set. And you can clearly see that this is the distance module, so the distance. You can clearly see that things that are very nearby are all more or less in the same zones, except of these ones that has more difficult to model characteristics. And what you want to ensure is that your observed things are well inside, embedded at least, your space of training sample. So this is a sanity check that is not doing a lot, but it's only data driven. So you just compute your input layers and you obtain this to have like a sanity check of some sort. Okay, this is to make sure that the neural network is not extrapolating. That's just this. So after that, you train your neural network and you run it on the sample of clusters. And of course, you try to compare with your colleagues that try the same way. And you try to compare the different parameters that you estimate in your work and see if you find something that is interesting. And here you have a lot of plots, I know, but here on the top you have the prediction, the comparison between our prediction and the one of Tristan, artificial neural network. This one is from Diaz, the one with the classical method, and then you have the another artificial neural network. You can see that you are missing a plot because they do not estimate metallicity in this case. And okay, from the vast things that you can see in this plot, there are something that is very important. You can see here you have a clear trend here in these two plots. In particular, young cluster here are reported to be older by our neural network. This is something that is really important. You also have these strange things that is just data visualization. It's not may appears that the neural network is drawing random numbers. It's just the dispersion that inflates a bit this plot. It's actually not drawing random numbers. But another thing is this one, large scatter at intermediate range here. You can barely see it because these plots are beautiful, but one thing that is very important is to look at the age distributions. So these are the age distribution of the various catalogs. You see here the plots. So you have the one from Tristan, Diaz, and Hamilton, and the one from our neural network. You can clearly see something also in this plot. It is very important. First of all, you see a clear peak here. That is from Diaz. That is in the range of the pre-sequence of open clusters. And they found pre-sequence of open clusters because their membership was polluted by a lot of contaminants. You see these empty dots here. A lot of faint contaminants that drives the model to fit this thing. That's why you also want something that is accurate and you do not want contaminants. Because this thing has been published and do not discussed and then rise up afterwards. We just spot it in our work. I know that someone is aware of this, but this is what is causing that spike. And so this is a thing. But another thing that you can clearly notice is the fact that Emily Hunt just produced a narrower distribution of age. And this is, of course, after close investigation of that, is only dealing with feature extraction method that you actually use to feed a neural network. Because they use like the method of compute an image and then feed to a convolutional neural network and so on. To compute the image, they need to pixelize the CMD and they divide it into 32 times 32 images. The problem is that if you carefully look at the pixel scale in the physical dimension, you're ending up with a pixel scale is like that. The lower part, of course, in color, the other one is in magnitude, ending up with this grid that I hope that you can all see. What is generating this grid is that you are losing information from the Gaia photometry. Because you can see here from simulated clusters that are in the age range of the peak, that all these clusters falls in the same column. Because the important thing is that the artificial neural network is not looking at this. It's looking at the column. So it's looking at the pixelized. So all these models, of course, these ones are without membership problems, without blue stragglers. So they are very clean compared to real things. And so the problem will go even in the worst direction. So what using this feature extraction, you actually lose a lot of information. And so your neural network becomes like not sure anymore in this particular age thing. On the other side, the PO3, that is the one that we use, you can clearly see that it works like an adaptive grid because it's computed cluster by cluster. So trace the position of the sequence and do not fall into the confusion limit of these two. These two are clearly different for the artificial network because it knows the clear position in the Coromine style. So after all these technical parts, I'm sorry, but are very important to fully understand what is inside machine learning techniques. We produce like a beautiful 3D map of the galaxy with age, extinction, distance, and things like that. And so we actually try to compare it with overdensity previously measured by Luisa Poggio. And here you have the clusters that are divided into age bins. Here you have the galactic center in this direction. And you can clearly see that very young clusters tends to clusterize in the spirals. Here you can see these overdensity are the spirals of the galaxy. And when you are moving to older objects, you are losing the initial position of these clusters. So they are losing the clusterization also in the 3D space. So this is something that is very beautiful.
So overdensity is based on what?
This overdensity, yes, sorry.
This
overdensity is based on massive stars.
But you mean the...
Yeah, the shaded area
shaded
here,
area.
the density map is based on massive stars, and the other points are open clusters. So they are tracing, we expect that they are tracing the same thing, but yes, it's cool to see this. Just do not look too much at this overdensity around the sun, but is all an observational bias, of course, because you find a lot of open clusters around you because it's nearby and easy to observe. And of course, you find less and less when you move on the outskirts. Yeah. No, all of them, because you see these ones, of course, not. These ones, yes, much more. Only the age.
Age?
Yeah, age. But it's just a visualization problem because these groups here are the most populated things. And so, yeah, it's something like that. And also as some measures, because we try to select only the intrinsically bright objects. So to remove something that is bright only because it's close by. But the brightness has also some scales with the age. So you are inducing some observational bias here, but the problem is not around the sun. We would like to see them tracing the spirals around in this like 4 kiloparsec, 5 kiloparsec space.
And your ones are fewer because they are not formed.
Yeah, exactly. You have the age distribution of clusters is also another thing that is a matter of debate. Can be for the star formation, can be for the dissolution. You find a lot of young clusters because probably at a certain point they dissolve if they are immersed in the disk. And so from the that distribution in age, you can infer the dissolution timescale. So you have also this dissolution problem. On top of that, you also may have a selection function problem that is tricky to address because, and we are trying to do it right now, but I do not have some results already. So we are trying to see the selection function of open cluster in Gaia, which is something very complex. Because for some zone of the galaxy, we expect also to have this with the dependence on the age, for example. The plot that I show you in the beginning, the fact that at galactocentric distance of 100 kiloparsec, you do not see young clusters, is because you do not have it, or is because your selection function is canceling them? That's an answer that we want to address because you see how complex is this thing. So having the data is not having the solution. You need to be aware to how to handle the data and to correctly account for selection functions that are very important. So gigantic seminar. I'm sorry for all the details, but I would like to let you that these models are like very beautiful, but they are dangerous because sometimes you can create something that is like in the overall picture seems like reasonable, but then if you look cluster by cluster, you find something that is very difficult to understand. So and then of course we proved with our work that the flow tree maybe is the future to extract the features from the column-wise diagrams because it's very powerful, and also the fact that maybe we should use multiple photometric bands to analyze these clusters because you can have you can remove some degeneracies between these parameters. And okay, then if you want more details, okay, we can discuss it. This is the article. You can write me to my email, and I thank you for the attention. And of course, if you have some questions, thank you.
Thank you, Lorenzo. We have time for a couple of questions.
Thank you. Regarding the tree, how many times do you subdivide, and do you have like a criterion to know? Because I could imagine that could introduce also bias, right?
Yeah, is like you fall into the complexity problem. So at some point, you do not extract any more informations. You are just producing noise at some point. So this is another tricky thing.
Mm-hmm.
So usually what you do, what personally I do in the first instance is to just try out some of them and look it in one by one.
So it's not the same for all.
No, it's the same for all. The depth of this thing should be the same because the input layer should be fixed, the dimension. So you need to extract the same amount of data. Now, up to now, I'm working on also on improvement of all this pipeline that use what is called synthetic photometry that is available in Gaia. I don't know if you are aware of, yeah, probably no, because I just got aware like 2 weeks ago. From Gaia, you can use the low resolution spectra to extract the photometry in other bands that are not directly measured for only bright stars. So these bands are like UV that are very powerful in the column-wise diagrams to disentangle between these parameters. Stronger, for example, than TrueMass because TrueMass is very noisy because it's infrared. And I'm also trying to study more these flow trees because like the ideal things that I would like to see is the fact that it's not tracing the whole bunch of points. It's tracing the lower left part of points. That's where the main sequence is hidden. So you can also play with the percentage. What if the division is not 50-50, but is like 60-40? You have also this thing, but it's a fairly new thing. So, but the powerful thing is that it's also with the dispersions of data. The problem is that instead of passing here, the isogram will pass a bit on the right of what you actually want. So I would like to push the extraction like a bit more further, but probably not more complex than this.
And just a quick related question. And
yeah.
What takes in terms of computing time?
This one?
Yeah, feature extraction. This one.
For the clusters is like 1 second. This one.
And what's for CNN?
For
the CNN.
Takes much more than this, because is why they do not use a smaller grid, because for the computational time, that's why they use only a 32 grid, and the problem is that to have this analysis of a convolutional neural network by dividing the in peaks of the image, you need to find a space where all the clusters are contained. So this one that is not that extincted, and also something that is very extincted. So these colors, BP minus R3, ranges from 0 to 6. In this case, you have only the clustering up to 1.8. So that's why the pixelization looks like too poor, because they need to deal with a gigantic space of big space of parameters, and they cannot divide it into more, because otherwise they go into complexity. So that's why PO3 is very powerful. It's very powerful, but it's something that we are studying now, because now I proved the fact that it's working. Now there is the optimization of that. So probably, I don't know where, but when, but because I'm finishing the PhD, so let's see how the future goes. But probably in the near future, we'll publish like an updated version of this thing. Yeah, the bottom line of this is like these models are beautiful, but we still need to learn it more by using them. And so probably there is a lot of room of improvement, also in the feature extraction and also in the neural network itself. On the training set, all these things can be improved.
If you enjoyed the video, like and subscribe.